The second lecture on asymptotics will be on exact bounds, lower bounds, and strict bounds. Just like we use big O notation to give asymptotic upper bounds on the amount of a resource that a computation may take, uh, we'll define big omega notation to give asymptotic lower bounds. We'll say T of n is big omega of f of n if there exists non-negative constants or positive constants and not in C such that for all values of n that are at least n naught, T of n is at least C times f of n. Okay, and so just like the big O notation we saw previously for giving asymptotic upper bounds, this big omega notation gives asymptotic lower bounds. In particular, we don't care what happens for small n, only after n is sufficiently large, we want that T of n is at least a constant times our function f of n. We'll also be interested in exact bounds. We'll say T of n is big theta of f of n if, and this time we won't have to give any new math, we'll just use the previously established big O and big omega notation. So T of n is theta, big theta of f of n if T of n is big O of f of n and T of n is big omega of f of n. Finally, we'll give two strict bounds. We'll give strict upper bounds and strict lower bounds. And these strict bounds are for saying that our function T of n grows strictly slower than or strictly faster than some function f of n. Okay, so we'll say T of n is little o of f of n if, and now we'll use the limit notation. The limit as n goes to infinity of T of n divided by f of n is equal to 0. And similarly, we'll say T of n is little omega of f of n if the limit as n goes to infinity of T of n over f of n is equal to infinity. Okay, so T of n is little o of f of n if T of n grows asymptotically slower than f of n, meaning eventually T of n is so small compared to f of n that its limit is 0. Similarly, we'll say T of n is little omega of f of n, but it's growing asymptotically faster than f of n, meaning T of n, the limit of T of n over f of n is infinity. Great. Let's look at a few examples of all of these notations. So to give some examples of big omega, n squared plus n is omega of n. It's also omega of 1, and it's also omega of n squared. In other words, the function n squared plus n is asymptotically lower bounded by n, it's lower bounded by 1, it's lower bounded by n squared. Okay, n squared plus n is also theta of n squared. Okay, but unlike before, n squared plus n is not theta of n, and it's not theta of n cubed. It's only theta of n squared. Okay, looking at our lower bounds, we could say that n is growing asymptotically slower than n squared, and we can say that n squared is growing asymptotically faster than n. Good, so those are a few examples of our asymptotic notation for lower bounds, exact bounds, and strict bounds. And so that's our discussion for this video. Coming up in the next video, we'll be talking about big O and the asymptotic analysis of logarithms.